So have a look at this graph. How would you find its equation? Yes, that looks a bit tricky, but what if I told you there's an easy way to do this? We can do this by knowing what cubics are. We can solve this by learning the equations of cubics. So welcome to my channel, Ozzy's Young Learning Emporium, and today we're going to be talking all about cubics. So, what does a cubic look like? This is how it looks like. Now, there's something to note. For a cubic, there are always three roots. So, depending on what characteristic we know of the cubic graph, we can calculate its equation. Let's start by looking at how our general form would look like if we knew the inflection point. So the inflection point is basically when the graph kind of turns. It's like that flat point we've got on the cubic where the graph is turning. So the equation for this, the general form, is y is equal to a in brackets x minus h cubed plus k. Here h comma k is going to be the point of inflection, and our a is going to be our stretch slash reflection kind of number. It kind of controls how stretched out your cubic is going to be or how it kind of reflects. So let's look at that on Desmos formula over here. So let's see what happens when we change our a. As I change it, as you can see, it is increasing, it's getting more squished. So it's getting less stretched, but as I decrease it, it's stretching outwards. And once we go into the negatives, look at how it has reflected from this to this. So this is how the A can control the reflection as well. And notice what happens at 0. When it's 0, that means this whole thing becomes 0, and that means y becomes equal to a constant, and since k is equal to 1, that is why we get a horizontal line at y is equal to 1. So this is what a kind of controls. So let's leave it at 1.4 for now. So now let's look at what happens when we change the h. So as you can see, h is for the horizontal. So you see this point over here is the point of inflection, and this edge is controlling how the graph is moving around horizontally. And this K, this is going to be controlling how it goes up and down. This is the vertical movement of the point of inflection. And notice when this is going to be, say, 5, you can see that right here it's 5. So the point of inflection, the y coordinate at that is 5. And same over here. If we move this to like 4, so over here, if we zoom in at 4, this is where we've got our point of inflection. So this is how these variables over here control our cubic graph. The second piece of information that we can use to form our equations are the roots. So for this, the general form is y is equal to x minus r1, x minus r2, and x minus r3. Again, over here, a is our stretch factor, our reflection factor, and r1, r2, and r3 are our roots of the cubic. Now, what are roots? When y is equal to 0, that is where the graph kind of cuts the x-axis. And at the points where it cuts the x-axis is called the roots. So in this example, our roots are going to be -2, 3, and 5. Now let's visualize this on Desmos. Root form in its general form over here. So I've given all of these variables a slider so that we can see what happens. So here, let's see what happens when we change the a. Similar things are going to happen. As we increase our a, the graph gets more and more squished. And as we make it smaller, it stretches out more. And once we go into the negatives, it flips around. So it reflects and it stretches. And when we reach 0, as you can see, this forms a line at y is equal to 0, because what happens is that once the a becomes 0, everything which is multiplying with a becomes 0 as well, and that is why we get y is equal to 0. So if I drew a line of y is equal to 0, it overlaps that one. So basically that's what happens when a becomes 0. So let's leave it at 2, and let's see what happens when we change root 1. So let's make our x 1 something like 4. Now notice what happens over here. There is this point where our graph cuts the x-axis at 4, 0. So this is our root, because over here our y is equal to 0, and that is the values of x at that point are called the roots of the graph. Similarly, if we changed our x2 and made it something like 3, now we can see that now we've got a root at 3. And since our x3 is equal to 1, we have got a root here, and root here. So this 1, 0 is our x3, 3, 0 is our x2, and 4, 0 is our x1, which can be controlled using these. And of course, these roots can be negative, because if we've got a root, say, at 2.7, if you look over here, we've got a root at 2.7. It can go into the negatives. This can be negative. This can be negative. Any of these roots can be negative. Even the a value can be negative. So this is how we can manipulate the cubic graph. Now that we know how to write out cubics, let's look at how we can generalize them. So here I've got an example where y is equal to 2x cubed plus 2. So our point of inflection is at 0, 2. And we're trying to keep the shape as it is. So that means the stretch factor isn't going to change. And we just want to move the shape around. And I'm going to show you how to generalize it so that we can insert variables such as a and b, and we can control a to change the height, meaning like where the cubic is, and b can change horizontally the position of the cubic. So that is what we can do with generalization, and let me show you how to do it. So here's how we can do this. What we've been given is this equation right here, which is a part of a cubic. Notice that we've been given that the highest degree, the degree is basically, I'll just write this over here, the highest power on a variable in an expression, in an equation. So here the degree is 3. So this is why it's a cubic. For a quadratic, the degree is 2. So that would be a parabola. But that's basically what a degree is. I thought I would mention it just so you guys know. But basically, now we need to generalize it in a way so that this graph right here, this one can be moved right, left, up, down easily by just entering two numbers, which is where how much we want to move it around. So something we need to consider is this is a part of a cubic, and because of this domain over here, it's restricted because this is saying that x cannot be greater than 0, which is why we don't see a cubic here. Sorry, not like that. It would be like that. We don't see a cubic there, which is because we've got this domain right here, and we've got another one which blocks it from going below. So this, because x cannot be greater than -1, which is why it is blocked like that. So now we just want to move around the shape with the same domain, like similar domain, so that we don't get a shape like this all of a sudden. We want to keep it this shape, and we just want to move it around. So how would we do that? This is actually quite simple. What we're going to do is use our point of inflection formula, right? So we know that a point of inflection is at h, k, and we're going to use this knowledge. So we're just going to write this out as this. So y is equal to 2x minus h cubed plus 2, because we had that plus 2, and I'm just going to add the plus k. So right now what we're going to have is basically the same graph, but we've been given these two variables which can actually help us move the point of inflection. Because if we change this, if we said it was something like 3, then this point would actually move 3 this way. Okay? And if we said this was something like 3, then what's going to happen is that this point is going to move 3 that way. And that is how we can change the location of this graph. So it's really simple from here. Now we just need to figure out the domain. So since we don't want this graph to be going further than this value here. We have this 0 here, which is this x value over here. So the x value, once we add in this, we use our variable because our domain is going to change and our x value is going to be h. Right now our h is 0, but if we added a h of 1, we're going to have to move in this direction by 1, and this is why our graph should then start from 1. So our graph would start from 1 and go like this, which is why we need to make our domain so that we've got h over here. Now x has to be less than h because imagine our h was 1, so our h needs to be less than 1. I mean x needs to be less than 1 because it needs to go in this direction. So which is why I'm going to say h is greater than or equal to x. Okay, and now we're going to figure out how to do our second bit of our domain. We cannot have this diameter, this little bit, this bit is going to stay -1. Okay, it's going to stay -1, and which is why we need to go ahead and do this. We need to go ahead and write h minus 1 because why? If this, so imagine this graph. Over here our x value is h, and over here our h value is h minus 1, and this is why we're having h minus 1, because the difference between this point and this point is going to be -1, and that is what we need to keep constant, and that is why our domain looks like that. So this is going to be our finished product. This is how it's going to look like at the end. So I'll just write that out more neatly. So y equals to x minus h cubed plus 2 plus k, and our domain now, we figured it out to be h is greater than or equal to x, and that is greater than or equal to h minus 1. And that's all. That's it. We've got our k, we've got our h, and we can use our h to horizontally move this graph, and we've got our k to move this up and down. So if I brought this into the center, we can move it up and down. And this is our original one. If I move this away, then this is the one that we've created. And yeah, that's how we can generalize graphs. Thank you so much for watching this video.